This is trigonometry, section 4.8, where we apply what we've learned so far to different real-world examples. And as we go through these real-world examples, there may be some new information that's brought up, some new things like the word bearings in terms of direction, and then things that like harmonic motion when we have oscillating frequencies. And you'll kind of see what we talk about, because sometimes with these word problems, it's really just making sure we understand the vocabulary so that we can answer the questions. One of the main questions or things that we're going to use, though, is to use SOHCAHTOA. So if you have not memorized SOHCAHTOA yet, make sure that you do, right? This tells me that the sine of an angle is equal to opposite over hypotenuse. Notice I've got an equal sign there. I have a fractional set up for each of my sides, and that theta represents the angle. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And they're kind of making sure that we know that sometimes they will denote angles as A, B, and C, where they are uppercase angles, and then the sides will be in lowercase letters. And let me show you what I mean. That first example is using a picture where we're using the angles as uppercase letters and the lowercase letters represent the sides. So we're going to find every single piece of missing information in this diagram. I know that the measure of angle C is 90 degrees, right, because it's my right angle there. And they tell me that the measure of angle A is 34.2 degrees. So how do I figure out the measure of angle B? Well, one of the main theorems that we know is that all angles in a triangle should add up to 180 degrees, and that's just a theorem that we need to know. So in order to figure out the measure of angle B, I just do 180 minus 90 minus 34.2, and I get 55.8 degrees. So we know this one over here is 55.8 degrees. Now let's figure out, say we want to figure out side A, and we have our angle over here, and we have this side here. Notice I only have the one side given to me. I cannot use the Pythagorean theorem unless I have two sides given to me. So in order to figure out one of the sides, I have to use SOHCAHTOA. And if I'm using 34.2 as my reference angle, A is the opposite side, B is the adjacent side, so I want to use a trig identity that uses opposite and adjacent. That's tangent. So I get the tangent of 34.2 degrees is equal to the value of A over 19.4. So in order to solve these, I'm going to multiply both sides by 19.4. I'm going to pick up my calculator and plug into it 19.4 times the tangent of 34.2 degrees. Make sure that you are in degree mode, and I get out that A is about 13.2. And of course, that's a rounded number. So when we're trying to figure out C, I'm going to go back to just using SOHCAHTOA, using the 34.2 degrees and the 19.4. But now I want to figure out my hypotenuse. So I need to say, okay, what trig identity uses adjacent and hypotenuse? That's cosine. So the cosine of 34.2 degrees is equal to 19.4 over C. Now, in order to solve for C, I know we've talked about it in class quite a bit, right? I multiply both sides by C. I then divide both sides by 34.2 degrees. The kind of shortcut is just to reverse those two pieces of data. So I get the side C is equal to 19.4 divided by the cosine of 34.2. So I pick up my calculator, should still be in degree mode, and I get that C is about 23.5. And there we go. We have solved for all the missing sides and angles in this picture. All right, our second example. Your book does like to include pictures in a lot of these diagrams, which you will have as well on the test question, so that's very nice. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. A fire department's longest ladder is 110 feet. What is the maximum safe rescue height? So if you're kind of living in this tower and you're saying, well, I'm up here on the top building, are those firemen able to get to me? Is kind of an interesting question, right? Are we kind of out of luck because we live on the top floor here? So let's figure that out. So here's kind of the diagram that shows your right angle here. You have this 72 degrees and you have your hypotenuse side, which is C. You're trying to figure out the height over here, which represents your opposite side. So what trig identity uses opposite and hypotenuse? Well, that's sine. So I get the sine of 72 degrees is equal to A, which they've flagged as our opposite side there, divided by 110 feet. Now, in order to solve this, I'm going to multiply both sides by 110. Very similar to our last question. I'm going to plug that into my graphing calculator, making sure I'm in degree mode. And let's round to 1 decimal place. I get 104.6 feet. So that represents the height of the building that is the maximum safe rescue height. All right, example 3. At a point 200 feet from the base of a building, the angle of elevation to the bottom of the smokestack is 53 degrees. Find the height of just the smokestack alone. So what we are trying to find, right, is just this height right here. The problem is the triangle that's kind of formed there is not a right triangle. So I wouldn't be able to use trig identities. But here's what I can do, right? I can use as much information as I possibly can to try to figure out what the height of the smokestack could be. All right? So I say, let's take a look at this smaller angle or smaller triangle that we have in here, okay? Let's look at right here. We're just going to look at this triangle right here. They've told us that the angle here is 35 degrees. I want to figure out what this side length A is. So I have my angle, I have my adjacent side, and I'm missing my opposite side. So I'm going to say the tangent of 35 degrees is equal to A over 200. We know from our previous questions that when we have this set up, I'm going to go ahead, we're going to multiply both sides by 200. Make sure I'm in degree mode, and I get that A is approximately, now I'm gonna keep all these decimals because I just want to make sure we are as precise as possible. So it's about 140 feet is that A value. Now let's go ahead and kind of erase what we have so far. Now let's take a look at the bigger triangle we have here, right? It goes all the way here, here, and here. So I'm going to use the 53 degrees now to say, okay, what is the full height, including the building and the smokestack added together? And then I'm going to be able to subtract off the building height, and it will just give me the height of the smokestack itself. So I have a very similar setup, right? I'm going to say the tangent of 53 degrees is going to equal that A plus S, right? I'm trying to figure out what that whole height of the building and the smokestack is over 200. Multiply both sides by 200. And I get out that the value of the building plus the smokestack is about 265.4089643. Notice I want to be as precise as possible. Now I'm going to subtract off our value of A. So I'm going to take this and I'm going to subtract it from this amount here. And when I do that, I get that the height of the smokestack is approximately, now we can go ahead and round. We're at the very end, let's round to 1 decimal place, is 125.4 feet. Moving on to question 4. A swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. Find the angle of depression in degrees of the bottom of the pool. All right, so this is kind of an interesting setup. First of all, this 12 meters wide, this is not important information. This is unimportant to our problem here. They're kind of telling you, maybe if we needed to calculate the amount of the volume of water that fits in the pool, we would need that information. But in this case, given our diagram here, we're just trying to figure out this angle here. And they've even told us, right, we've got the 1.3 meters, that's the shallow end, but then 4 meters at the deep end. So I've got this extra, right, 2.7 meters that's going to get me to the bottom of our deep end there. So I need to really just focus in on the important information, and the picture definitely helped, which is this small triangle right here. I want to figure out the angle. I have the adjacent side is 20, and my opposite side is 2.7. And notice both of them are in the same unit, so I'm doing okay there. So I'm going to go ahead and use tangent. The tangent of theta is equal to my opposite side over my adjacent side. Now, in order to solve this, right, I have to use my arcsine or our arctangent or inverse tangent function. I'm going to have to use those inverse functions in this case. So that ends up kind of canceling out the tangent on the left-hand side. So I get theta is equal to arctan of 2.7 divided by 20. And let's get the angle in degrees, because that's what the question asks. And normally with word problems, we're going to want our answer in degrees. So let's go ahead and plug that into our calculator, making sure we are in degree mode, because that's what we're looking for. And I get 7.7 degrees. Didn't say what to round to, but let's make sure we pay attention to that. In this case, let's again, just like our previous examples, we'll round to 1 decimal place. All right, so examples 1 through 4 are definitely examples that I would expect us to have seen in similar classes, maybe in Algebra 2 or Geometry, but now we're going to get moving on to some things that are slightly different, probably things that you have not done in your previous classes. The first is bearings. So say you are in the military or an avid sailor, you like to get out on the water. Bearings is something that you'll come across. I think hopefully we all kind of understand our north, south, west, east notation, but how do we really explain bearings? So on one of your homework questions, it simply says, I can't remember the exact angle, like an airplane is flying at a certain speed and it has a bearing of, let's say, 40 degrees. If it doesn't give you any type of direction and it just says a bearing of 40 degrees, well, that implies that it is 40 degrees to the east of north. So if it doesn't say anything, that is what you have to assume. You're doing 40 degrees east of north. So if you see a homework question like that and it doesn't explicitly give the directions in terms of north, south, west, or east, that is what kind of the default is. Now, otherwise, it's going to give you kind of the specific details. For instance, the bearing south 35 degrees east is going to say, okay, start at south. So here's our south, and then we're going to go 35 degrees to the east. And that becomes important when you're trying to figure out, well, do I need that 35 degrees? Do I need the 65 degrees that's left over here? It's just, how do I draw it on the coordinate plane? That's why we need to be able to kind of understand those. This one here in the middle, let me make sure we can see it all. Down here, the picture seems to not be showing it all. This one right here is north 80 degrees west, right? Notice I started at the north line and then I went 80 degrees to the west. This one over here, south 35 degrees east. This last one over here, north 45 degrees east. Very similar to kind of that example I originally showed there. So now that we have a little bit of an understanding about bearings, let's go ahead and look at a problem to solve it. And again, I really like that your book gives you a lot of pictures to try to help sort through this information and see a diagram of it. So a ship leaves a port at noon and heads due west at 20 knots or 20 nautical miles per hour. So the way that they measure speed on the water is slightly different than the way we do it, say, in a car. But we've gone for 2 hours, which means we've traveled 20 nautical miles. And then another 20 nautical miles, so we've gone 40 nautical miles in total. At 2 o'clock, so right around here at 2 p.m., we reach this point. The ship changes course to north 54 degrees west. So even though we're out here and we're turning, we're kind of turning to the right, we consider everything from the north here. So we're 54 degrees west of where north is. So I know that this angle here is 54 degrees, just as they've shown you. The ship then goes another hour, so it's gone another 20 nautical miles, and we want to figure out, say we're calling back to kind of our port or home here, how far away are we from that port, which is represented by the letter A, and then what would the bearing look like? What if we kind of call it in, we know we're going to be west of north, but what is the degree that we are west of north? Basically, what is this degree value here? So we've got a lot of different things we got to figure out here. The first is let's figure out our distance from A. Okay. Now, in order to do this, we've got a few things that we got to figure out here. The first being is I kind of want to know what this big triangle is. There's going to be a lot of pieces here, right? I want to figure out this big triangle. I'm going to use that to help me figure out what the length of my hypotenuse C is. The only thing is, I don't know what B and D are. So I've got to figure those out using this information that I have. I know that my hypotenuse for this smaller triangle in here is 20. And I need to figure out, okay, what's this angle amount here? This whole thing is going to be 90 degrees. So if this is 54 degrees, then this smaller angle here is 36 degrees. So let's go ahead and figure out both the B and the D values. So first, we'll start with the B value. I want opposite. I have hypotenuse, so I'm going to use the sine. So the sine of 36 degrees is equal to B over 20. And multiply both sides by 20, pick up that calculator. I get that my B value is about 11.76. And yes, we probably don't really want to round, but at this point, let's just make sure we can fit all this on this page here. So I know that that now is 11.76. Now let's figure out the D value. I want adjacent, I have hypotenuse, so I'm going to use cosine. So I get the cosine of 36 is D over 20. Again, multiply both sides by 20. And I get that D is approximately 16.18. So that down here is 16.18. Okay. Now let's figure out our C value. Well, the entire side down here, let's figure out what we got here. Here we go. Got all these different things. I want to make sure it doesn't get too cluttered here. You can see it a bit better. So I know this whole side length right here is going to be our 16.18 plus 40. So I've got 56.18 is this whole length down here. And I know that our side over here is 11.76. So what I can do is I can do the Pythagorean theorem to figure out how far away we are from port. So I do 56.18 squared plus 11.76 squared equals our C value squared. We also could have used SOHCAHTOA if we wanted to, found the angle first, and then done it that way. Let me go ahead and grab my calculator, plug this in. I get that our C value is about 57.5 nautical miles by using our Pythagorean theorem. So I know that I'm 57.5 about miles from our port. Now I want to figure out what this angle is here so that I can subtract from 90 to get the distance from north. So let's go ahead and we'll use tangent because I've got here, but again, there's so many different ways to do this. Tangent of that angle is equal to the opposite side, 11.76, over my adjacent side, 56.18. I've got to take my inverse function. I'm going to wrap that around there. So I get theta is approximately, let's round to one decimal place, just like we did last time, 11.8 degrees. So that tells me if I do 90 minus my 11.8, it's 78.2 degrees up here. So if I were to kind of radio this in, or hey, we're out here in an emergency situation, we need help, our bearing is north 78.2 degrees west, and we are 57.5 nautical miles away. So that kind of answers all of that question. Hopefully we can kind of see through all that chicken scratch. Lots of different ways to do this, but we had a lot of information to fill out with that question. All right, our last topic is harmonic motion. So think about our sine and cosine functions, right? They go up, they go down, they go up, they go down. That type of frequency, that type of pattern comes up quite a bit in terms of things that vibrate, oscillate, rotate, move in some type of wave motion. So for example, think about, we've got a spring and we'll attach a ball to it. And here's kind of its picture as it's sitting in equilibrium. We then we pull it all the way down to the maximum negative displacement that we can. And then this represents the maximum positive displacement when it bounces right back, right? And it gives it that spring value to then bounce out. So suppose that 10 centimeters is the maximum distance the ball moves vertically upward or downward from its equilibrium. Suppose further that it takes time for the ball to move from this maximum displacement of 0 to its maximum displacement below 0 and back again is 4 seconds. So that tells me, right, it goes to its maximum and then minimum and then back, right? Because it's going to eventually fall to our equilibrium type thing, or at least kind of travel that distance to get back to the equilibrium. Suppose, right, we're living in a world with no friction, no air resistance, no anything like that. Obviously, a normal sine curve that would model this would have a lot of extra things added in. We are just going to model this by using a sine curve. And the reason why we're going to use a sine curve is just thinking about the shape, right? At time 0, it's starting, kind of the distance that it's traveled is 0. So think about a sine curve. We start at the origin at 0, 0. So we're going to want to use a sine curve as we model this. So our period, it took 4 seconds to complete that period. Our amplitude, which is the distance between our maximum and our minimum divided by 2, is 10. And we do about 1/4 of a cycle per second. So this is kind of our simple harmonic motion. And we have a formula that we give to this. Notice it looks very similar to the formulas that we've seen before, right? Before we had A sine bx plus c plus d, right? That was kind of our, minus c. But Those are the equations that we've seen before. These are the exact same. They just seem to have replaced these kind of letters that we're using. Do not worry about it. It's the exact same thing. And even when we figure out our period value, we do 2 pi divided by b, divided by the number in front of t. Okay, so let's try to figure some of this out, right? Let's try to write an equation for this. So I know that we're going to use sine, right? We just talked about why we're going to use sine for that value. We figured out that our amplitude is 10. Our period value, 2 pi divided by, I'm going to make that a b, so I know when students see all those Greek letters, they kind of freak out a little bit. It takes 4 seconds to complete that. So what does my b value have to equal? Let's multiply both sides by b. Right, so I get 2 pi is equal to 4b, and then we're going to divide by 4. So I get b is equal to pi over 2. Now I just plug that into my equation using, right, the distance equation that they've set up. So 10 sine pi over 2 t, where t is our time that is given. And that is it. Do not let that overwhelm you if you see a question like that. You're really just trying to plug this information in and get out your answer. Thank you for your time.